Okay, thank you for being here today. I'm Sonya. I work at the Australian Antarctic Program Partnership, and I'll be talking about clouds. But before we get into why I'm interested in clouds in the Southern Ocean, I'm going to explain to you how a cloud is formed. So, for a cloud to form, three conditions need to be met. I need a microphone. Yep, okay. Three conditions need to be met. First, we need to have water vapour, so water in a gas phase, in the air. The second condition is it needs to be cold enough for that water to want to condense, so to turn to a liquid. Water won't just turn into a liquid of its own will, okay? It needs a surface to condense onto. Okay, so that's our third condition, is a surface, and these surfaces are provided by aerosols, so tiny solid or liquid particles that float around in the air. So if we have aerosols in the air, it's cold enough, and we have the water vapour, a cloud droplet can form. So I have a video here taken by one of my colleagues. He was right next to the Antarctic coastline on the Investigator. It was very cold, it was very dry, there wasn't a lot of water vapour in the air, and it was very clean, so there weren't a lot of aerosols. We have a teacup here providing water vapour, and when I play the video, you'll see we introduce a source of aerosol. What you'll notice is before we introduce the aerosol, you can't see anything coming off this teacup. But as soon as we introduce the aerosol, we can see the cloud droplets forming, basically. So that is how a cloud is formed.
That's cool.
Yep. It's a nice little experiment. So why do we care about aerosol-cloud interaction? Aerosol-cloud interaction is the most uncertain aspect of modelling our Earth's energy budget. So what I mean by energy budget is sunlight comes in to the planet. Some of that sunlight is reflected back out to space. Some of that is re-emitted as long-wave radiation, but that's basically our budget, how much comes in and how much goes out. So we can see carbon dioxide has a positive radiative forcing. Radiative forcing is what governs changes in temperature. And then we see aerosols and aerosol cloud interaction have a negative radiative forcing. So they actually cool the planet, have offsetting carbon dioxide. But what I want you to notice on this slide is the size of the error bars. Okay, so aerosols and their interaction with cloud are much more uncertain than what we know about how carbon dioxide influences the energy budget. And that uncertainty impacts things like our temperature projections in the future. You know, if you want to project sea level rise, all of these are made more uncertain because of our aerosols and how they interact with the energy budget. So how does this actually come about? This is a plot. It's the bias of the Australian climate model, ACEAS, in how much sunlight it reflects out to space. So what we're interested in, this is for summertime, what we're interested in is this big band of blue that goes right around Antarctica. That's showing that the ACEAS model is not reflecting enough sunlight out to space, which allows too much sunlight to reach the surface of the ocean. And you can imagine what impact that has on the rest of the Southern Ocean system within the model, warming ocean temperatures, sea ice. So this is the challenge that we have. So my title was Supercool Clouds. What is a supercooled cloud? A supercooled liquid water cloud is a cloud that remains liquid even though the temperatures are below freezing. So you might think that as soon as temperatures get below 0 degrees, that the cloud droplets will freeze. It's a good assumption, but it doesn't occur that way. The type of aerosol that that cloud droplet formed on will change whether that droplet can freeze or not. So aerosols that are good at freezing clouds are things like dust, things like air pollution. Aerosols that aren't good at freezing clouds are things like sea spray and sulfate aerosols, from which there is a large source of sulfate aerosol produced by marine biology, like phytoplankton. So in the Southern Ocean, there aren't many sources of pollution. There's not a lot of terrestrial influences either from dust. So we have more supercooled liquid water clouds in the Southern Ocean than we have anywhere else on Earth. Why is this important? If we go back to this plot, Our models were mostly developed in the Northern Hemisphere, and in the Northern Hemisphere, this assumption that there's lots of dust or lots of pollution is generally okay. I wouldn't say it's right, but it's okay. But in the Southern Ocean, it's not. It's not okay. But our climate models don't know this. So in our model, we have too many ice clouds. An ice cloud will let more sunlight through to the surface, whereas a liquid cloud is more reflective. So this is where this problem stems from. Our models don't produce enough supercooled liquid water clouds. So as part of our work at the AAPP, we have increasing evidence that it's these biologically produced aerosols that are being produced in highly productive sea ice regions of Antarctica that are essential in producing these highly reflective clouds, these highly reflective supercooled liquid water clouds. So I have two plots here. The first one here shows the Antarctic coastline, East Antarctic coastline, and the red and yellow colours are places where there are often lots of cloud droplets. So the more cloud droplets you have, the more reflective a cloud is. So this is from a satellite, and we can see that it's right next to the coastline that this occurs. So we have clouds with lots and lots of droplets. The second plot is from a ship campaign, and we've got an aerosol size distribution. So we have the size of aerosols along the x-axis, and the number on the y. When we take an observation from a ship, we can then use model products to understand where that air came from. So we can trace it back and say, this air has mostly been over the ocean, or this air has had contact with the Antarctic continent. So that's what the two colours are. An air that was mostly over the ocean, we can see it has lots of aerosols, but they are too small to form clouds. Whereas air that has had some contact with Antarctica and has lots of these biologically produced aerosol have still lots of aerosols, but they're much bigger and they are good at forming clouds. So we can see the evidence stacking up that these biologically produced aerosols are really important for forming these supercool liquid water clouds in our models. Not in our models, in reality. We're trying to tell our models to do this. So this is part of the work that I do. We've seen the top figure already. The bottom figure is where I ran a simulation of the climate model and I told it to do a better job of marine aerosols. And this is the improvement that we found. So we can see we've improved the region of that blue area to reduce the radiative bias over the Southern Ocean. And this was just the first step, so I think we can do a lot more to improve this model. And we're also working on the forecast models as well. So with that, I'll end there. Thank you.